Okay, we've been learning about scientific notation and how it helps us to read, write, and compare numbers that are very, very large or very, very small. And it just gives us kind of a shorthand and makes those numbers easier to work with. The other thing that we need to think about, though, is our choice of unit. So if we make sure we're using the correct units, even those very large and very small numbers can be a little more manageable. So let's start with a simple example of a table. So we have a table and we want to know how to measure that table. I want to communicate to you how big this table is. So I could tell you that the table is 60 inches long. And that might have some meaning to you. You kind of know how long an inch is, and you know, maybe you can picture 60 of them, okay? I could also tell you the table is 5 feet, and that might even be easier for you to imagine than 60 inches. But what if I told you the table was 1/1056th miles? You know, if I measure this table in miles, it's nowhere near as meaningful. So we wouldn't want to use miles as a unit to measure a table. It's pretty obvious, but it is what we're going to be talking about in this lesson. Okay, then the first 3 exercises, I'd like you to take a couple minutes and just look at each of them. Each of them ask you to determine which unit would be the most appropriate for the given situation. So start with exercise 1, but work on 1 through 3, and then come back and we will work on those together. Okay, exercise 1 asks us about the unit of time. Okay, so we've got 1,000 songs on an MP3 player, and the average song length is 4 minutes. So I've done the math up top here. And so that would be 4,000 minutes of music. And I want to be able to think about, okay, how much time is 4,000 minutes? I mean, is that going to give us, you know, days of music or just hours of music? And so I want to do some conversion because that number isn't particularly meaningful to me. But our problem is asking us to figure it out in terms of seconds, days, and years. So we'll do at least that. Okay, so if I want to know how many seconds of music I have, I need to convert minutes into seconds. And I'm going to use a method called I'm going to find a conversion factor, and I'm going to use unit analysis basically to calculate this. So I'm starting with 4,000 minutes, and I'm going to find a unit multiplier. So this is my unit multiplier here, and that is 60 seconds over 1 minute. And I really could put in a 1 there. 60 seconds over 1 minute. So that's a fraction where the numerator and denominator are the same. So it's equal to 1. All right. So I can multiply by this and not change the value of 4,000 minutes. And when I do that, I get 240,000 seconds. Okay, and obviously 240,000 seconds is less meaningful to me than 4,000 minutes. So I'm going to go the other direction. So if I look at 4,000 minutes, this time I used 2 unit multipliers. I've got 4,000 minutes that I'm starting with. I'm going to multiply by 1 in the form of 1 hour over 60 minutes. And then that would give me how many hours of music. So 4,000 divided by 60 would tell me how many hours of music I have. But I'm going to go ahead, because the problem asked me to do days, I'm going to go ahead and multiply by 1 day is 24 hours. So what's happening here is I want my units to cancel. So I've got them like this. Anyway, this is how I do unit conversion so that I don't make a mistake. I carry the units along, multiply by a conversion factor, and then figure out what it is. So to do this one, I took 4,000 and divided it by 60 times 24, because this is just really one big fraction right here, isn't it? So I get 2.8 days. Okay, well, that's pretty meaningful to me. I can wrap my head around 2.8 days. It's almost 3 full days of music, 24-hour days. So I could have that thing playing 24 hours a day. All right, so what is 2.8 days? What is that in years? Well, let's look at that. So 2.8 days, in order to get a year, to get that number in years, I'm going to divide by 365, or I can think of it as multiplying by this unit fraction, or conversion factor here. 1 year over 365 days is equal to 0.0077 years. Okay, so obviously the most useful of these would be to measure the music in days worth of music. The other one that might be helpful would be to stop at hours, which we didn't calculate, but it would be 24 times this. So we could do hours, but days is a handy unit too. Okay, so let's look at exercise 2. In this one, you are asked to make frosted cupcakes to sell at a school fundraiser. Each cupcake contains about 20 grams of sugar. Bake sale coordinators expect 500 people will attend. So everyone's going to buy 1 cupcake. Does it make sense to buy sugar in grams, pounds, or tons? And explain. Now, you didn't necessarily need to do any math for this one, but I did some for you. So I calculated that 500 cupcakes, because each person's going to buy 1, times 20 grams of sugar per cupcake, per 1 cupcake, I should have put here. And so that's 10,000 grams of sugar altogether that we're going to need. And so I was asked to talk about grams, pounds, or tons. 10,000 grams is a little hard to wrap my brain around, especially since I don't know the metric system. And so I converted it into tons. So it is 1 over 10 squared, or 1 over 100 tons. 1/100th of a ton, which also has no meaning to me. I can't quite picture that. So I would go on, and I'm going to take the 10,000 grams and convert it into pounds. So the conversion factor I'm using is 1 pound is equal to 454 grams. And that's an approximate conversion factor because pounds and the metric system and the standard system don't really talk to each other. So this is an approximate conversion factor. So I'm going to get an approximate answer right here. That's why I made these wavy right here. So 1,000 or 10,000 grams of sugar is about 22 pounds of sugar. So I know that I can buy, 5 5-pound bags of sugar, and I'll have plenty for my cupcakes. So it would be the most appropriate unit there, would be pounds. All right, let's look at exercise 3. So the seafloor spreads at a rate of 10 centimeters per year, approximately. So if you wanted to collect data on the spread of the seafloor each week, what unit should you use to record your data? So obviously they're using centimeters to record the yearly data. So let's think about weekly. So let's look at, so here's a centimeter ruler. So 10 centimeters per year is about the amount that the seafloor spreads. So that's about 4 inches, roughly. But each month, if we think about it, it's less than a centimeter per month because there's 12 months in the year, obviously. So less than 1 centimeter per month. And so that wouldn't be a really good unit because I would be using decimals to describe it. So we could use millimeters to describe how much per, because there's 10 millimeters in each centimeter. So if I used millimeters, I would have numbers that would be easier to write and compare than if I measured it in centimeters or even kilometers or something like that. It would be ridiculous. Okay, let's move on. Okay, our next example comes from the field of particle physics. So particle physics is where we're going to study things like protons, electrons, neutrons, which we'll study this year in 8th grade science, but also mesons and muons and other types of particles. The photo right here, the picture right here is the what was traced out from two protons colliding in one of these particle accelerators. So those are some really interesting patterns and things. So it's a really interesting field of study with lots of practical applications. But they're dealing with very, very, very small things. So a new unit was created so that the numbers that they work with make more sense and are easier to read and write and do operations with. Okay, so we did some examples before, and we saw that the mass of the proton is this number here, on the order of 10 to the negative 27 kilograms. And the mass of an electron, did I say electron or anyway, proton and electron, is this number, 9 times 10 to the negative 31. So on the order of negative 31. So electrons are quite a bit smaller than protons, as we saw, about 2,000 electrons to equal the mass of a proton. So kilograms is not a good unit to measure this in. Kilograms is what we measure body weight for humans in. So that's probably not the best unit. So it could be argued that, well, maybe we should use grams, because grams, there's 1,000 grams in 1 kilogram. So maybe using grams would be better. But even if I use grams, the mass of a proton is on the order of 10 to the negative 24 grams, and the mass of an electron is still 10 to the negative 28. So that's not really that helpful to convert my measurement of protons and electrons into grams. It's really, I'm still in huge exponents on my scientific notation. So a new unit was devised, and it's called the Giga electron volt. And it's just a really small unit. So you can see in your notes here that it's defined as, right here, it's a unit of mass, and it's defined as this, 1.783 times 10 to the negative 27 kilograms. And then the mass of one proton is repeated here for us. So in exercise 4, we're going to show, by converting the units, we're going to show that the mass of a proton is approximately 0.938 giga electron volts. Okay, so 0.938 is really close to 1. So it kind of makes sense, because if you look at these two numbers here, they're very close. 1.7, 1.6, they both have the same power of 10. So they're going to be very close. And if you're wondering about this c squared down here, this unit is actually used for mass and energy. So if you look at, remember Einstein and E equals mc squared. So if I divide both sides by c squared, I would get E over c squared is equal to mass. So that's kind of what's going on here. This is giga electron volt, sounds a lot like energy. So c squared, c is the speed of light. So that's what this number down here is. But you don't need to really concern yourselves with that, because here we're using it as a unit of mass. It is a very, 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 very small unit of mass. All right, so using the method of finding a unit multiplier, I'd like you to verify that the mass of a proton is 0.938 giga electron volts. So go ahead and pause the video here and work on that. Okay, so there's our mass of a proton, 1.622 times 10 to the negative 27th kilograms. So what I need is a unit multiplier that I can multiply by so that kilograms cancels and giga electron volts is left. So my unit multiplier is going to look like this. It's going to have giga electron volts in the numerator, and it's going to have kilograms in the denominator. So if you look up top here at this equality, 1 giga electron volt is equal to that number there. So that's what I've written right here. So that's my unit multiplier. That number, as crazy as it looks, is equal to 1. So I'm just multiplying by 1 to get this in a different form. Kilograms, there's kilograms in the numerator, kilograms in the denominator, so it cancels. So the only unit I'm left with is giga electron volts. And so when I do the math here, I end up with this fraction. So I've got the mass of the proton in the numerator, the mass of 1 giga electron volt in the denominator, and I want to simplify that. So my units are going to be giga electron volts. And when I do the simplification, notice that 10 to the negative 27 over 10 to the negative 27 is 1. So those become a factor of 1 and so cancel out, so to speak. So I just need to do this division right here, and a calculator for this is great. I don't want to do division with all those decimal places. So this can go into my calculator. I don't need to worry about the exponent because I've taken care of that, and I get 0.938 giga electron volts. Okay, so we just talked about a new unit that is a very, very, very small unit of mass. So in the field of astronomy, we're dealing with long distances and large masses, so we need different types of units for that so that we can just simplify our calculations even more. So here's a diagram. These look like orbits, but they're not. They're just showing distances from our sun. So our sun is here, and if you've ever heard of the Oort cloud, that's where that's the region where they think comets originate from. So this is just outside of our solar system. I believe it's outside or right at the very edges of it. And so these other things out here are stars, and the closest one to us is Proxima Centauri, and its distance is basically 4 times 10 to the 13th kilometers. So quite a large distance away from us. So we're going to talk about a unit now that will help us measure large distances in galaxies. Okay, so here in your notes you have this, and it says there's a unit called a light year. And light year is the distance that light travels in 1 year. So 1 year is 365 1/4 days. But a light year is that really, really big number, kilometers, 9.46073 times 10 to the 12th kilometers. So now work on exercise 5 and see if you can do this conversion. We want to convert the distance of our nearest star from this unit given in kilometers, which was on our diagram on the other page, to light years. Okay, because light years is a unit of distance, and so we can, that's much larger than a kilometer. Okay, so let's convert that to kilometers. Okay, so let's start with the distance of Proxima Centauri from the sun, and it's that many kilometers, 4 times 10 to the 13th approximately. And I want to write a conversion factor that's going to give me light years in my final answer. And so that's my conversion factor. That's the equivalence. A light year is 9.4 and some digits times 10 to the 12th kilometers. So the way I've set it up, kilometers is going to cancel. So when I do the math, I can think of that first distance as a fraction over 1. I'm going to multiply across, and I'm going to end up with 4 times 10 to the 13th over 9 times 10 to the 12th. About. I didn't give all the decimal places there. My unit here is going to be light years, okay, because that's what's left in my numerator here. I've got light years left, and so now I just need to straighten out the numbers here. So if I work on these separately, and again, I would do this, the 4.01, all the way out to 6473 divided by 9.46073 on a calculator. The second part of it simplifies really easily for me. It's the 10 to the 13th over 10 to the 12th is 10 to the 1st, right? So basically what I've done is, get a different color here, is I did this part and then this part. First part I can do on my calculator. This part is simple, 10 to the 13th over 10 to the 12th. I'm dividing numbers with the same basis, so 13 minus 12 is 1. I'm left with just 10. This number comes out to about a half, right? I could have kind of estimated that there. But I don't want to leave it like that because it's very simple to put it in decimal notation and it's easily recognizable. So I've got 4.2421 light years. That's how far away our nearest star. So that's light would take four and about a fourth years to get to Proxima Centauri. So let's go back and look at our diagram that we had on the previous page, and there it is. So this this ring here shows 4 light years, and this is just beyond, just a little beyond 4 light years. But that's the closest star. The closest star doesn't get light from our sun for 4 years from the time it leaves. Pretty interesting. All right, so let's keep going here. Okay, this next example is not in your notes, but we're going to talk about the mass of objects in our solar system. So we've got the sun and all the planets. Now Pluto's not a planet anymore, I know, and you're going to have a question about that on your end of module assessment. So there were some reasons why they decided Pluto shouldn't be a planet. One of them had to do with its mass. So let's look at, oh, they threw in the moon here too. So we've got the sun, the planets, and our moon, Earth's moon, right here in this chart. Okay, so these are really large numbers. I clipped this picture off the internet, so the exponents look a little funky here, but I think you can figure this out. This is 10 to the 30th, 10 to the 27th, and so on. So the magnitude of these masses is pretty big, on the order of anywhere from the smallest of 10 to the 22nd up to 10 to the 30th for our sun, 10 to the 27th for Jupiter. Okay, so if I was going to define a new unit for mass for talking about the masses of objects in the solar system, I might look at this chart and base my decision on some of these numbers here. So as I look at these numbers, I notice a couple things. If I look kind of in the middle, I see these planets in the middle anywhere from 10 to the 24th, 10 to the 25th. Neptune, Uranus, Earth, Venus. So those are all kind of a similar order of magnitude. There's some smaller and some bigger. So if I'm going to define a unit, I might want to pick something that's kind of in the middle. Another reason that I might pick one in the middle is because that's our Earth, all right? And Earth is right there kind of in the middle mass-wise of the planets. So that's actually what happened, and this is an actual unit, It's called an ME. 1 ME is the mass of the Earth. And so 1 ME is equal to the mass of the Earth, which if you look on the chart is 5.9736 times 10 to the 24th kilograms. All right, so let's look at a couple examples where I'm going to convert some of these other masses from kilograms into MEs. So let's look at one of the planets. Let's look at Jupiter and convert Jupiter's mass from kilograms into MEs. Okay, so the Earth is 1 ME. That's the definition of an ME, right? So what I want to do is start with Jupiter's mass. So here it is, 1.8986 times 10 to the 27th kilograms. I want to create a unit multiplier. And here it is, 1 ME is the same as 5.9736 times 10 to the 24th kilograms. So that's a factor of 1, which doesn't change things. Kilograms cancels. And so I'm left with this calculation to do. So when I do this calculation, I'm going to do it in two parts. I'm going to do the decimal part of my scientific notation separate from the power of 10 part. That didn't look good. Separate from this power of 10 part. So what will that look like? Well, I get 0.318 when I put this into my calculator. Makes sense because this is about 2, this is about 6, so 2 6 is 1/3, and that's pretty close to this decimal right here. All right, and then the power of 10 part gives me times 10 to the 3rd, 27 minus 24, it's my exponent of 3 here, and my units is MEs, because that's what I'm left with up here. So I've got 0.318 times 10 to the 3rd MEs. Because this is a pretty reasonable number, I'm just going to rewrite this as 318 MEs. Okay, so what do I mean when I say that Jupiter has a mass of 318 MEs? Yeah, so it means that if I took 318 Earths, that would equal the mass of Jupiter. So that is a really useful unit. It makes so much more sense than looking on this chart at these huge numbers in scientific notation. Okay, so it kind of seems like we taught you scientific notation and then we're showing you a way to not use scientific notation. So in a sense, that is what we're doing. But we still need the scientific notation to get to these units and to be able to convert back and forth between them. So it's not useless, but you can see how important it is to have the correct unit when you're working with something. Okay, so we could use the same process and find out how many MEs all these other planets are. And you could actually look that up online. A lot of the tables will have the mass in MEs instead of kilograms. Okay, so the last thing here to do is this exploratory challenge where you're researching atomic diameters and you end up with these measurements here. So what this exercise asks you to do is just what we did in the last example with the MEs, but it asks you to do it for really small numbers here. So there are no really right or wrong answers here. You get to determine the new unit and you get to even name it. So you can do this if you feel like you need a little bit of extra experience with this, and then you can check in the teacher's edition for what some of the answers were for that. But if you feel pretty confident in converting to units like this, then go ahead and move on to the exit ticket and or the problem set.